Right, so this is the mirror board that I like to use, and you've definitely seen it before. Okay, guys, just to keep things very clear, in the last term, we have gone through organic chemistry, and for this term, the current term, we'll be doing, I would say, physical chemistry. So yeah, basically we finished organic chemistry already in the last term. But I think as emphasized many times, everything, whether organic chemistry, physical chemistry, and even stuff from your last semester, everything will be covered in your final exam this semester. Which is I think the dates are not finalized yet, so it should be in week 19 or 20. All right, so guys, I remind you again, make sure you are serious about everything that we have gone through, because everything would be covered in the coming exam, including last semester's content. Now, yep, let's start. So as I said, this term is about physical chemistry, and there are 3 chapters. Not sure whether you have gone through the content. So the first chapter is what we call energy changes. The second is on rate of reaction, and the last one would be on redox. Okay, maybe I just quickly write it down. So basically, there are 3 major topics for this term. Okay, so this would be the first one. Second one would be on rate of reaction or speed of reaction. And the last topic will be on redox reactions. Now, I think right off, I have to let you know the hardest topic I think based on experience so far will be this one, redox reactions. That is why we leave it to the last. For energy changes and rate of reaction, I expect everyone to do very well for these 2 topics, because they are considered I would say, the easiest for this whole semester. So, but well, of course, as per normal, if you have any questions along the way, to just voice out and ask, or you can type in the chat box, even though I can't be looking at the chat box all the time. Now, back to this energy changes. Now, I have actually given out you the outline right here on the mirror board. It essentially boils down to only 7 elements here. Okay, 7 elements for this topic on energy changes. Now, okay, to make things very simple, energy changes can apply to either a physical process or a chemical reaction. So, let's just be very clear. Okay, so just be very clear. I didn't really write this out, but energy changes can apply to a physical process or a chemical reaction. So don't be surprised if you see questions about physical process. Now, what is meant by physical process? Let's ask somebody. Clarence, are you there? What's a physical process?
I don't know.
You don't know? That is covered in lower secondary school.
I forget.
Oh, okay. Then let's ask Don, are you there? Don, what's a physical process?
Uh,
Or you can give some examples.
like
Oh,
burning.
burning. Ah, okay, come guys, let's be very clear, even though we have kind of touched on this last term. No, physical process, if you make it sound very lame, basically it's not a chemical reaction or a biological reaction. So that means there's no chemistry involved, no biochemistry involved. Yeah, I know it sounds kind of lame as a definition, but that should make it quite easy to digest. So examples, all your changes of state are physical processes. Yeah, guys, please try to remember all this. These are covered in your lower set. So changes of state will be your melting, boiling, condensation, freezing. Okay, I don't think I need to write them out. And there are others as well, like for example, dissolving, or I'll use the word dissolution. Yeah, it's a physical process when you dissolve something. Crystallization. Hopefully you guys still have some inkling of what these processes are. All right, so these are physical processes. Now, just now Don was speaking about burning. Burning is combustion. Okay, guys, reminder, make sure you are very clear about the word combustion. Combustion is basically burning, and it is essentially a reaction with oxygen. So, yeah, make sure you really know the term burning or combustion is a reaction, or okay, a chemical reaction with oxygen. So burning is definitely not a physical process. Now, of course, we have gone through many others. Oxidation, which we have gone through last term, is a chemical reaction. And if you still remember your N levels, precipitation, okay, I don't think I want to go through every single reaction, but essentially you get the idea. So, to make a long story short, whether a physical or a chemical process can give rise to a energy change. Okay, so, oh, by the way, these few words, please recognize the changes of state. In fact, I think I'll write that out later. All right, changes of state, boiling, melting, freezing, condensation, sublimation. Yeah, because you may see them in your exam. That's why I want to emphasize on them. Okay, let me just try to shoot them a bit off. Okay, so as per normal, anyone has any questions? Yep, please ask. So now with that out of the way, there are two words everyone has to know. I'm pretty serious. These two words, you definitely see them. All right, exothermic and endothermic. Now, in fact, it's quite, I'll try to get it right the first time. Okay, what's exothermic? Exothermic means heat is released or given off by a process. Okay, yeah, please get it right now. Don't confuse the two terms. Exothermic heat is given off. Okay, so what else? What else? That also means what? That also means temperature of the system increases. Yes, don't confuse yourself. If it's an exothermic process, temperature increases. Yeah, just stick to this fact. Okay, don't confuse yourself. Yeah, maybe I'll tell you later why some students get confused, but for now, just take it as it is. Exothermic means temperature increases, heat is given out. Okay, simple as that. Oh, by the way, of course, the word thermic, the Exothermic means heat, though you don't really have to know it. Well, it's the Latin for heat. Well, probably you can deduce what endothermic means. So endothermic is the reverse. Heat is absorbed by a process. And that means temperature of the system decreases. So your MCQ question may ask you, temperature decreases in this direction. What kind of process is it? Immediately, you should figure out that it is referring to an endothermic process. Now, I think as I was saying earlier, okay, process. Again, don't be too fixated on this word process. Process can be a chemical process or a physical process. So yeah, so you do not it's not always just referring to a chemical reaction. A process can be a physical process too. As I said, it has definitely come up before in the exam, so make sure you're familiar with the process being a physical or a chemical one. Yeah, that in fact, these two words, that's all you need to know about these two words for now at least. Okay, then, oh, as I said, anyone has questions, just voice out. Okay, there's the third new word that you have to know, something called entropy. Okay, to make a long story short, what is entropy? You do not need to define it, but to understand it, this entropy is basically heat. Okay, even though there are, I would say, more detailed definition, but there's no need to go into those. So for now, entropy, just take it as heat. And what else? There's a symbol for it. Hey guys, make sure you know the symbol or you recognize the symbol. Right. Entropy is always represented by capital H. Okay. And guess what? Entropy has units too, which of course you have to know. What are the units for entropy? In fact, you guys should know. You should have learned it before. Ziming, are you there? What are the units for entropy? Or what are the units for heat? Ziming? Missing. Edison? Yep, Edison, what are the units for entropy? Oh, well, then you can just type it out. Now, as I was saying, entropy is, well, you can take it as heat. What are the units for heat? Oh, nobody remembers. Okay, good try. Clarence mentioned K. Okay, guys, come. Let's be very clear about a few things, huh? Okay, good. At least Ashad got it correct. Now, as I was saying, enthalpy is heat. So the units will be heat units, guys. All right, units will be the joule. So the short form, make sure you can recognize the short form as well. It's capital J. Again, I have to emphasize I'm not writing all this out for fun. You are expected to know all this. All right, and of course they are likely to come up in your assessment. So enthalpy units will be joule. Okay, just now Clarence was talking about K. Try not to confuse yourself. K stands for Kelvin. Kelvin is not the unit for heat. Alright, K stands for Kelvin. And Kelvin is the unit for temperature. So what I want to impress upon all of you, temperature is not the same as heat. So make sure you don't confuse the two. Alright. Now temperature is yeah, I know it means the degree of how hot it is or how cold it is, but temperature is not the same measure as heat. Okay, heat is a unit for, heat is energy, but temperature is just the level of hot or level of cold. But again, we will not go too much into that. Just make sure you don't confuse yourself. Enthalpy units units is joule, not Kelvin, not degree Celsius. Okay, so yep. Okay, what else? What else? Guys, try to pay attention because this I want to write something new here that I'm not sure whether you've come across. Now, there is something called enthalpy change. Or sometimes they rephrase it as change of enthalpy. So yeah, I think there's no big deal. What's enthalpy change? Yep, try to not write this down, even though you won't be tested like this, but it's going to help in your understanding. So what's enthalpy change? And it means final enthalpy or final heat level minus initial enthalpy. That is enthalpy change. Trust me, you will see this term in your assessment, enthalpy change, and make sure you know that is the final minus the initial level. Okay. Now, what else? Enthalpy change is represented by delta H. Okay, yes, please write this down. You will definitely see this. As I said, enthalpy is H. And here, I'm interested in the change. So you tag on this triangle in front. All right, so the triangle is pronounced as delta. Okay, therefore, enthalpy change is also called delta H. Yeah, make sure you get used to it. Delta H means enthalpy change. So in the exam, you will either see this, you will either see enthalpy change, the words enthalpy change, or you will see delta H. So make sure you know that they are the same thing. Okay. Okay. Right. What else? Yeah, guys. Yeah, if you have any questions, do voice out right now. Okay, it's hard to judge from your appearance whether you have any questions or not. Okay, I will go on, but of course, if you have any questions, you can either voice out, you can type out in the chat box. Okay. So far, what we have covered 3 concepts. Exothermic, endothermic, entropy. Okay. Now, of course, I also mentioned about the differences between physical process and chemical process. As I said, they are supposed to be your secondary school content. So, yeah, make sure you know them. I mean, to me, they are, in fact, to you, they are not supposed to be new concepts. Okay, the fourth concept is this one here. All right, energy diagram. There are a few, I would say, a few expressions for this term. Sometimes they call it energy level diagram, or they call it enthalpy diagram. So yeah, and I would say that almost 95%, there will be there will be a diagram of this sort coming up for your exam. Okay, so what does it look like? Let me just erase some stuff first. Okay, energy diagram. Now, I mean, for your syllabus, there are 2 kinds. It's not not exothermic and endothermic. I mean, there are 2 kinds of 2 representations. Okay, the first kind of diagram will be the easy one. So it looks like this. Okay. Let's just give you an example. So let's say I have this reaction. A becomes B and C. Okay? Yeah, let's just take it as a chemical reaction. So how can you draw an energy diagram for this chemical reaction? Okay, maybe I just write down as well. This is a chemical reaction. So what I can draw is okay, let's have one more constraint here. So this reaction, the whole reaction is considered exothermic reaction. Okay? Okay, so when A becomes B and C, heat is given out and temperature of the whole system increases. Okay, exothermic. I mean, yeah, let's assume it's exothermic. So how do we draw the energy diagram? It's going to look like this. Okay, so basically, I put one horizontal line, put A here. Okay, then I draw another horizontal line below B and C. Okay, so what happens? Oh, okay, before I go further, what do these horizontal lines mean? So this line means the initial entropy. Okay, remember left hand side is initial, right hand side is final. I mean, that is the convention that we tend to follow. But as I said, we are drawing an energy diagram, so this is the initial entropy or initial energy level, even though try to use the word entropy. And of course, this second line below is the final entropy. So what does that mean? It means I can add in an arrow here. Yeah, remember the reaction is from A going down, proceeding to produce B and C. So initial, okay. What do you notice from this diagram? The implication is this. It means my initial, or let me use short form, HI, and initial enthalpy is greater than final enthalpy. Okay? Yeah, because it's higher, that's how we by convention, when it's higher, we draw it higher up. Okay? So of course you have to follow this convention. But what else? What else can you tell me about this enthalpy diagram? Remember this? Delta H? What can you say about delta H? And just to refresh your memory, this is delta H. Okay? Enthalpy change. Final minus initial enthalpy. Okay? It's always, I don't care what reaction, what process. Enthalpy change is always final minus initial. Okay, let's go back here again. So, yeah. What can anyone tell me about this delta H enthalpy change for this reaction? You already know that this reaction is exothermic. So enthalpy change is final enthalpy minus initial enthalpy. Yeah, nothing new. We mentioned this earlier. What else? What else is new? Look at this again. My initial is greater than final. Huh? The value is greater. Huh? So what does it mean? It means that my enthalpy change is negative. Guys, make sure you highlight this point. Delta H or enthalpy change is negative. Yeah, this is important. And also that implies any exothermic process, you have a negative delta H. So yeah, make sure you highlight this. This is super important. In other words, if I tell you that a process has a negative delta H, yeah, it implies that that process is exothermic. So it can go both ways. Exothermic means negative delta H, or you're told that negative delta H implies that the process is exothermic. Yes, please jot this down. This is important. Oh, the diagram too lah. As I said, this diagram here, this one here that you see is the easier, is the, I would say, the simpler one, which is less likely to come up. Okay, the one you see here. Okay, this is the entropy diagram. This is the easy one, but most of the time you won't be asked about this one. There's another version that you need to know. So anyway, anyone has questions, just voice out. Okay, so that was for exothermic. Endothermic. If I tell you a reaction is endothermic, how's the diagram going to look like? Actually, you can probably draw out yourself by now. Endothermic. Let's have another chemical reaction. So let's say X plus Y give you Z. And you know that this is an endothermic chemical reaction. I mean, we assume it's a chemical reaction here. So yeah, back to our question. How do you draw the energy diagram or the enthalpy diagram for this one, this endothermic reaction? Hopefully some of you have figured it out by now. Which part is the initial? This is initial. Initial always refer to the left-hand side. So this will be my final. So just look at this again. This one is exothermic. I think most of you should figure out that the endothermic will be somewhat reverse, right? So how to reverse it? It is going to look like this. This is my initial enthalpy. Yeah, remember you need two horizontal lines. And this is my final enthalpy. Now, let's be very, I would say, clear. Obviously, don't have to draw this in, but as I said, going upwards means increasing enthalpy. That is always the convention. Please don't reverse the convention on your own. Upwards is always increasing. So therefore, what's the initial? What's on the initial line? Yeah, initial will be your components on the left. X plus Y. Final, as I said before, final will be your component on the right. So this will be Z. Arrow. How do you draw the arrow between these two horizontal lines? It's always from initial to final. Again, in case you haven't noticed, over here, the arrow is going down, whereas over here, the arrow is going up. Okay, so that is one of the differences between exo and endothermic reaction. Okay, what else? What else can you talk about this endothermic reaction? Now, you need to mention about delta H as always. How is the enthalpy change, or how is the enthalpy change? So delta H is always final H minus initial H, always, because you look carefully here. Delta H here is final minus initial. Guess what is the same for here as well? Final minus initial. Okay, but what is different? What do you notice for this energy diagram? What is the, how do you compare between final and initial values? I can write this thing down. Final enthalpy is greater than initial enthalpy. For the simple reason, final is higher than initial, so I can write this statement down. And therefore, I can safely say that delta H, because final value is greater than initial value, so delta H is going to be greater than 0, which also means, oh guys, this is important. In case you miss out everything earlier on, at least note this down. Delta H is positive. Let me use the words. And that brings us to the moral of the story. for an endothermic reaction, meaning heat is absorbed from the surroundings. So temperature is dropping down in the whole system. That implies that delta H is positive. Okay, so this part is, make sure you get it right. Endo always means delta H is positive. I mean, of course, you can write as positive or you can write as bigger than 0. Whereas exothermic means that delta H is negative. And again, in the exam, they may write this. In fact, most likely they will write this less than 0. So make sure you recognize that this is negative and this is positive. Okay, questions, anyone? Yep. Hopefully you notice. So this is the energy diagram for endothermic reaction. But unfortunately, your exam will not ask. No, I would say the chances of getting you to draw this is pretty low. These two diagrams. You will be drawing something more complicated than these two. Okay, unfortunately. So yeah, later I'll just show you the diagrams that you're likely to be drawing. Okay. Oh, by the way, I think I want to go back to something earlier on. Okay. Let's look at exothermic. All right. Just now we said that is heat is released. You can feel the heat, no? Of course, because temperature is increasing. So if this reaction is exothermic and you are near to this reaction, you can feel the heating up process. That is exothermic. So what are examples of exothermic process or exothermic reactions? This one you guys have to know a few at least. I'll give you one. Please write down, please write down. Okay. Examples, the best example for, let's say, chemical reaction is combustion. If it's a combustion, 100% confirm it's an exothermic process. Yeah, you may be asked this in your MCQ. You have a few choices. Which of the following is an exothermic process? So make sure you recognize combustion is an exothermic process. Okay, so one of the answers may be a combustion. So example, combustion, hopefully you haven't forgotten your last term's work. Let's say I have my alcohol. Your alcohol combusts. Let me again emphasize, you need oxygen for combustion. And what are the products? This alcohol here. Oh, by the way, guys, hopefully you haven't forgotten the name of this alcohol. It combusts. What are the products you will get? The end, what products will I get? The end, what are the products for combustion of that alcohol?
Carbon dioxide and water.
Okay. Okay, good enough. So CO2 and water, make sure everybody knows how to balance this, by the way. Okay, I'm not going to balance this now, but you are supposed to know. All right, so this is a combustion reaction. Yeah, automatically, don't have to think, it gives out heat. So it's an exothermic process or exothermic reaction. But sometimes combustion can be a bit, I would say, less obvious. I'll give you another example here. Now, guys, I hope that you can remember and recognize this second reaction is a combustion too. But in this case, H2 or hydrogen is combusted. And of course, you get water or water vapor or steam, whatever that is over here. So yeah, make sure you recognize this is a combustion too. And what is important is make sure you also recognize this is an exothermic process. Okay. Maybe I'll just give you one last example of combustion. Of course, as always, I'm not writing all this for fun. Because yeah, you really may meet these reactions. One more example. Even this one. Yeah, what's happening here? Carbon, you know what's carbon? Carbon is essentially coal or charcoal, and you burn it in air, meaning that it reacts with oxygen, you get CO2. This is a combustion too. And as I said, a combustion is always exothermic. Heat is given out. I think that's quite easy to visualize. I mean, you burn something, you can imagine heat coming up and you can feel the temperature increasing too. So think along that line. So, yep. Combustion is one example. Questions, anyone? Now, the other one that I want you guys to know, okay, let me do some shifting first. Huh? Okay, the other chemical reaction that I want you guys to remember being exothermic is this one. Neutralization. I mean, no doubt, I don't think you have put your finger inside a beaker during neutralization, but essentially it gives out heat. Okay. Oh, by the way, make sure you know what is neutralization. Ma, what is neutralization? Turn on your mic. It's still not turned on. Still can't hear you. Yep, try speaking again.
Hello.
Yeah.
Acid plus alkali.
Okay, great. Guys, of course, I'm not going to revise that now, but make sure you recognize what is acid, what is alkali. So neutralization, I'll just write it down here. Acid plus alkali, but of course, if you want to be general about it, it's actually acid plus base. Okay, so yeah, I repeat, neutralization. Your basic HCl plus NaOH, and which you are supposed to know how to complete this equation. This is exothermic. Neutralization is always exothermic. Again, I can't go into too many examples. Okay, so there are others, of course, but make sure you remember this too. Combustion, neutralization, they always produce heat. They always raise the temperature. of the entire system. But let's cover the other one, the other examples for exothermic. Now, the other important examples will be changes of state. This one, all of you must know. Yeah. So when is heat release? It's not so obvious, no, because you don't really yeah, probably you won't be there to observe the temperature or something like that. But let me try to gather my thoughts. Okay, this one can be a bit tricky because the temperature may not change. But anyway, you're supposed to know that these changes of state are exothermic. So for example, condensation. That means from a gas or a vapor, it turns into a liquid. Okay, actually heat is given out, but you probably can't feel the heat. It's a bit different from combustion where you can definitely feel the heat. Even neutralization, if you try to hold the beaker where you have neutralization going on, you probably can feel something. But condensation is a bit hard because the heat is diffused. You won't really feel that. And of course, the other one will be freezing, in which liquid becomes solid. Okay, so this two can be quite tricky. As I said, it has definitely come up before. The reason is they are not so intuitive. I mean, how often do you think of condensation as giving out heat or freezing as giving out heat? You just put everything in the freezer and that's it. Do you actually put your hand inside to actually measure the to try to feel the heat coming out? No. So these two changes of state are a bit counterintuitive. But yeah, you're supposed to know these two processes are physical and they are both exothermic. Okay, yeah, as I said many times, this has come up before, unfortunately, so you have to know that. Now, let's go to the other examples for endothermic process. Again, let me try to shift some of the stuff. Oops. Okay, never mind. I think I'll just draw out. Okay, endothermic. I try to draw further outside. Endothermic means heat is absorbed by the process. Let's start with changes of state. Now, as I said earlier, changes of state are physical processes. Just now, condensation and freezing are exothermic. So for endothermic processes, what are they? Well, some of you probably figured it out. They are the opposite. Just now we had condensation. So now we have the opposite, which is boiling or evaporation. I think this is easier to visualize. Imagine you have your liquid, oh, by the way, you should know this, liquid to gas or liquid to vapor. Imagine you have a liquid. What is happening? The liquid is absorbing the heat. All right. whether the heat is from the surroundings or you supply the heat yourself, liquid is absorbing the heat in order to become a gas. Okay, so that is why boiling or evaporation is endothermic. How about freezing? Just now we mentioned freezing as exothermic. What is the opposite of freezing? You guys better know the answer to this. Ernest, what's the opposite of freezing?
Melting.
Okay, good. Oh, it's, by the way, it's primary school stuff. But of course, you guys are supposed to know this. Melting is also endothermic. Imagine your solid. Absorbs heat. It becomes a liquid. So that is melting. Oh, by the way, just a reminder, endothermic means heat is absorbed. So in this case, your solid is absorbing the heat to become a liquid. Okay, I just want to introduce one last change of state, which may or may not come up. Okay, the last one is sublimation. Okay, just add this in somewhere, even though it may or may not come out. Sublimation simply means a solid goes straight to become a gas without converting to a liquid. So that is sublimation. I mean, you just jot this down somewhere, even though it may not come up. Okay, questions, anyone? No? Oh, yes, before I forget. For endothermic, we also have some other processes which are endothermic. It's not so common, but this particular one, let me just zoom in. Dissolution of certain salts. Okay, that means not all kinds of salts, but certain salts, when they dissolve in water, you can feel the whole beaker turning cold. Maybe you have tried this before. Again, I won't go into too much detail here. What are these salts? What are these certain salts? Just a couple of examples. One is, of course, ammonium chloride. There's no need to remember, but just keep this somewhere in your mind. Certain salts, when they dissolve in water, the whole system turns cold. The other one is ammonium nitrate. Okay, so maybe just one last thing. Endothermic. Oh, but just a quick reminder. Change of state is a physical process. Dissolution is a physical process. So far, I haven't mentioned any chemical reaction yet. I'll just give a couple examples. So for chemical reaction, what is an endothermic? Okay, again, this one is not very intuitive because you don't really sense the temperature decreasing. Okay, one of them is actually photosynthesis. Yes, by the way, guys, photosynthesis is a biochemical reaction. The other one also, I won't say, in fact, it is not very common, but I mean, as in, it's not common in the exam. The other one will be thermal decomposition. I'm not going to write out the examples because this is not exactly commonly seen in your syllabus. So just jot this down because this can still come up when they ask you, like I said in the MCQ, which of the following is an endothermic process? So maybe one of the answers is photosynthesis. So you may just have to, yeah, choose the correct answer. Oh, by the way, what's the opposite of photosynthesis? Anybody can remember?
Respiration.
Excellent. So guys, can you just jot this down? For exothermic, I didn't add this in just now. Maybe you can add it in now. Let's add this in. So for exothermic chemical reaction, you should also include, I mean, strictly speaking, it's not a purely chemical reaction, it's a biochemical reaction, but nevertheless, you still need to know respiration is exothermic. Okay, so photosynthesis is endothermic. The opposite is respiration. Respiration is exothermic. Okay, so just jot this down, even though this is not guaranteed to come up. Okay, questions, anyone? No? Okay. I'm not going to complete this whole topic today, of course. I think that would be too much or too overwhelming for you to follow. Hopefully, it's not too overwhelming now yet. But let's get back to just now, this thing here, the energy diagrams. So this diagram is for exothermic process. This diagram is for endothermic process. Now, let's say if I give you another process. Yeah, expected to draw. Okay, yeah, expected to draw the energy diagram. Even though this is the simple one, as I said, you are not likely to be asked about the simple one. You're probably going to draw a more complicated one. So anyway, let's give you another example. So let's say I have this physical process. Physical process. Let's say condensation. Okay. Now, I think if you refer to what we have written earlier, condensation, in your head, you already know that is exothermic. Condensation is always exothermic. So how are you going to draw the energy diagram? Well, first of all, you have to figure out what is condensation. So basically, condensation is from a vapor, or use the word gas instead, gas to liquid. Yep, so I think we can all agree that this is condensation. So next, how do I draw the energy diagram? I leave it up to you, but for me, how do I remember exothermic? Exothermic is always downwards. Endothermic is always upward arrow. I mean, that's how I will remember it. I leave it up to you to decide how you want to remember it. So since this is exothermic, is a downward arrow. So therefore, yeah, I just go ahead, draw a downward arrow. So I draw a downward arrow. Now, the arrow is important because it tells you what's initial, what are the initial state and what's the final state. So it's always from initial to final. So is the arrow always represents initial towards final, always. What should you write on the initial level? Remember, initial is always on the left. Final is always on the right. But of course, you can also straight away just follow this arrow as well. I hope you notice. You just, instead of left to right now, the arrow is from top to down. Okay, so I just add in. So gas is here. Liquid is below. As long as you remember, for exothermic is a downward arrow. So now I have my energy diagram. Okay, but let's, I think for good practice, this is the initial enthalpy. I'll add in the word enthalpy. This is the final enthalpy. And of course, the enthalpy change, usually they will ask you to write this out. Enthalpy change, all right, is negative. Okay, remember, if it's a downward arrow like this, enthalpy change is always negative. I can, of course, do the same for this as well. So let's say we have a physical process. Now, I don't think I want to explain that much now, but I'll quickly draw this out. For example, melting. Now, as we said, melting is always endothermic, always. Okay. All right, it's always endothermic. Okay. So therefore, look at here. Oh, how is the arrow like? Upward arrow. Okay, before that, let me flash up the example. So in this case, melting means from solid to liquid. Again, how I remembered it, endothermic is an upward arrow, so make sure I draw an upward arrow. Notice solid to liquid. So likewise, I also put solid to liquid. Okay, so this would be the initial, this is the final enthalpy, and this is the initial enthalpy. Okay, F for final, I for initial, and then you need to write out what's the enthalpy change. Remember, enthalpy change is final minus initial. So in this case, it's always positive because it's an endothermic process. Okay, so that's my energy diagram. Okay, questions? Okay, but unfortunately, as I said, this is a simple energy diagram. In the exam, they'll likely ask you to draw a more difficult one. Yeah, please try to follow because I would expect this question to come up for your exams. How to draw an energy diagram. Not this one, but the more complicated one. Okay, so let's use this example. So, how do I draw? Yeah, all these are still valid, but just that the diagram will look different. Now, the diagram looks like this. I'll write it down. More complicated diagram. Okay, more complicated energy diagram. So I'm still using this example here. this exothermic example, I'm still using A, reactant A breaks into products B and C. So yeah, try to follow. I need to draw the two axes. Oh, I repeat, I am expecting this to come out. Either the exothermic version or the endothermic version, either one of them. Okay, it's going to look like this. Okay, remember this. I'm pretty serious. I would say like I said earlier, I think 90 to 95% this is going to come up. This is for exothermic, but you notice I haven't labeled anything, so make sure you label. X-axis is progress of reaction. Or sometimes, yeah, you can put it as time as well. Y-axis, okay, same. Just like this, just now, when we drew this diagram here, what is the vertical axis? Is energy level or enthalpy if you want. Okay, just put a H here, make it simple. All right, so guys, remember H stands for enthalpy. We have already mentioned that right at the beginning. But what about all these other things? Now, then what's on the left? The initial, right? Initial component or the reactants. So A is here. So A is here on the left, right at this horizontal line. What's on the right? B and C. These are the products. B and C are here. Hopefully you notice A corresponds to A here. B and C corresponds to B and C there. And you notice A is always above B and C because this is an exothermic reaction. Okay, what else? We are not done yet. You have to add in some more labels. Now, if I draw a straight dotted line and a straight dotted line extrapolated from B and C, what is this? What is this? The height here, what is this height? Or what is the difference in height? Now, I hope you notice as well. This corresponds to the height difference. Okay? Oh, but of course, so what? What does that mean? It means that this is my delta H. Why? Because remember the dotted lines? This is my H initial. This one here is my H final. So this final enthalpy, this is initial enthalpy, and of course the difference should give me the change in enthalpy or enthalpy change. Yeah, guys, you are supposed to draw or label all this in your own diagram to get the full marks. Okay, one last thing. Let's use a different color. How about this thing here? Why is there a hump right here? What is this? Okay, I just tell you the bare essentials. I'm not going to elaborate any further, this thingy here, note, is what they call activation energy. There's a short form for that, even though you don't really have to remember. Okay, so it's EA. And notice what is activation energy. Let me just write down, even though you won't be asked in this manner. Okay. Basically, activation energy is equals to the maximum entropy. Oh, by the way, this is the maximum. Minus of the initial entropy. This is the initial entropy. Okay, so the height difference between maximum and initial will give you activation energy. Yeah, this is the mathematical explanation, but how about the physical explanation? What is activation energy? Okay, guys, this one you have to know. Okay, this one here is not so much in your syllabus, but it helps you in your understanding. But what exactly, or what's the physical meaning of activation energy? Okay, guys, just try to follow. This would be, I assure you, this would be the last concept I would touch on today. What exactly is activation energy? Okay, energy required by the reactants to proceed with the reaction. Oh, I mean, just a small detail here, lah. Probably you realize it, but let me be very sure. Activation energy, of course, the units are joules as well. Okay, it goes without saying. Units should be joule. Okay, likewise, let me change the color. Likewise, for delta H, units are also joule. Okay, so make sure you're clear about that. Oh, of course, I mean, they are all based on the entropy or the energy levels. Energy is measured in joules. So activation energy is energy too. So it's also in joules. Delta H change in entropy or change in energy is also joule. Yeah, so make sure you don't mess up about the units. Okay, so yep. Okay, so essentially you in the exam, I suspect that you will be asked to draw this diagram here. Okay, they'll tell you that this is a exothermic reaction and they ask you to draw the energy diagram. So this is a default one that you need to draw, the complicated version. Hopefully I haven't lost anyone. Any questions from anyone? No? No? Then in that case, I will finish up with the last concept for today, which is the energy level diagram or the energy diagram for endothermic reaction. Okay. How is it going to look like? Okay, so we use back the same example, this one here. Oh, just a note, huh? For this complicated version, the one here with the harm and so on, this complicated energy diagram only applies to a chemical reaction. Okay, because if it's a physical process, then there's nothing to draw. A physical process will simply be just like that, the simple version. Okay. I mean, obviously you'll be asked to decide lah, but normally they'll give you a chemical reaction, and then this is the one that you're expected to draw. Okay, the only question I would say the only uncertainty is for your exam is the exothermic version coming out, or is the endothermic version coming out? I don't think both versions are going to come out at the same time. So yeah, so therefore you have no choice. You have to learn out both. Okay, let's go to the endothermic version. Now they'll give you, yeah, same thing. They give you a reaction, maybe something like this. X plus Y give you Z. So how do you draw the energy diagram? Just now we drew the simple version. But as I said, the exam will expect you to draw the complicated version. So yeah, you have to know how to draw it. So let's go through step by step. That's my start. Now again, I'll base my answer on this example reaction here. First thing, what do you draw? Axis. And what is the x-axis? Anyone can remember? X-axis is? Ashad, what is x-axis? This one, x-axis. What is my x-axis? Yep, Ashad.
Is it time?
Okay, time is fine. Or progress or reaction. Let me just write it down. Oh, guys, you're supposed to write all this in your exam answer. But of course, to me, writing time is easier. However, sometimes the question, you must also be versatile enough to recognize if your question use the term progress of reaction. Make sure you understand that it's referring to time. Now, how about y-axis? What is my y-axis for this energy level diagram? Who is that? Sujit?
Yeah.
Yep. What is my y-axis?
Temperature.
Temperature. I think we have not touched on temperature much. Now, guys, make sure you put this as energy or enthalpy. Please do not write temperature. You will definitely be penalized. Okay, Sujit, take note. Okay, what else? Now, my reaction is this. X plus Y give me Z. So, and what else do I know? Z is at a higher energy level. X plus Y is at a lower energy level as we have drawn in the simple version earlier. Okay, guys, this is how it looks like. Make sure you remember that. Okay, this figure here is for an endothermic reaction. Recognize it, remember that you may need to reproduce it. Now, as always, what's on the left is, remember, time is always from left to right. So likewise, look at my reaction. What's on the left? X and Y. So just put X and Y here. And what's on the right? Right is my product. So as time moves from left to right, Z will be, or my product will be here. But of course, I'm using this as an example. X plus Y gives you Z. You must be flexible enough to recognize if it's a different kind of reaction. Make sure you put reactants here on the right, on the left, I mean, and the products on the right. Okay. What else? Remember just now we did also extrapolate the dotted line. So this is initial. Yeah, because it's at the beginning of time, so it's initial. Okay, initial enthalpy. And this is, we can also draw another dotted line here for this horizontal portion. Z is at the end. Remember, Z is the product. So this is my final enthalpy. And of course, what is this height difference here? Yeah, height difference is between initial and final enthalpy between HF and HI. So that is the enthalpy change. Okay, and look at what we have drawn earlier. This one here. HF is higher than HI. Yeah, of course, one. HF is higher, is above HI. So that means delta H is positive. So likewise, we can write the same here. Delta H is positive. Remember, this is an endothermic reaction. Okay, yep. What else? One last thing to label, guys. One last thing. Where's my activation energy? Look at my mathematical definition. This is my definition or mathematical definition of activation energy. Maximum H minus H initial. Okay, so go back to my diagram. Where is my maximum H? Here. Okay. Okay, maximum H is here. And where's my initial H? Well, right here. Initial H. So this whole horizontal line is my initial H. I mean, of course, it extrapolates from this point. Right, it extrapolates from this point, initial H. So this whole horizontal line is my initial H. So if I take the difference, between max and initial H, this gives me activation energy, or this is the official symbol, capital E small a for activation energy. So yep, you're done. That's all you need to label. But as I said earlier, sometimes, I mean, this is based on my example here. This example. Okay, it's based on this reaction. X plus Y gives you Z. In the exam, well, you won't know what kind of reaction you're given. So let me put some generic labels. So in other words, reactants should be here. Then on the ending horizontal line, product should be there. Okay, so this will give you your full marks for energy level diagram or energy diagram pertaining to a chemical reaction. But of course, make sure your question is telling you that this is an endothermic reaction. Okay, because this pattern is for endothermic. And you compare to the other one, whereas this pattern, I hope you can see the difference. This pattern is for exothermic reaction. Please check the question carefully. Is it an exothermic or an endothermic reaction? And you draw accordingly. Questions from anyone? Now, as I've said, the link to this Miro board is given in the chat box right at the beginning. So if you want to go back into this Miro board or you want to do a screenshot or whatever, you can do so. All right, rather than trying to review the whole video recording. I mean, this will still be there. Well, at least for the next few days before I erase it for another class. Okay. So just a very, very quick summary of what we've done today. We have gone through the topic on energy changes. Okay, number one, first concept, make sure you know the word exothermic. Heat is produced, temperature rises. Okay, so that's meaning of exothermic process or exothermic reaction. And of course, the opposite will be endothermic. Heat is absorbed by the process, and as a result, the system is cooled down, temperature drops. So that is endothermic. Yes, please do not screw up on these two definitions. The third concept is entropy. Entropy simply means heat. Guys, even though it's beyond your syllabus, not say beyond your syllabus, this is something you have learned in the past, but you're expected to know the difference between heat and temperature. All right, heat is energy. Temperature is just the degree of being hot or the degree of coldness. And entropy, make sure you recognize the symbol is capital H, units, joule. And also, if we speak about entropy, we also can speak about entropy change or change of entropy, delta H. So make sure you recognize it, delta H. Delta H means final heat or final entropy minus initial entropy. That's why we call it change in entropy or entropy change, delta H. You definitely see this. Okay, same thing, delta H units will be joule as well. All right. Okay, lastly, we did mention this part about energy diagram. So sometimes they call it energy level diagram or sometimes they call it entropy diagram. These three terms refer to the same thing, so do not be confused. And of course, you're expected to draw for both. I mean, usually for the exam, one of this will come up, either exothermic or endothermic. And of course, for exothermic, it's going to look like this. This is the full version. Make sure you have the y-axis labeled, x-axis labeled, and it looks, I mean, the pattern follows this curve here. Make sure you label delta H between the initial and final. Make sure you label activation energy, which is right here. Okay, likewise, this is the version for endothermic reaction. Okay, same thing, y-axis is still the same, x-axis is still the same, it's still time. All right, except the curve now look different. Okay, again, label this difference between the final line and the initial line will give you delta H. And difference between the maximum point and the initial H, which is HI, this will give you the activation energy. Okay, so make sure you label all this correctly and you get your full marks for the energy level diagram. We touched on some examples, but I'm not going to go through them now. Make sure you have jotted all this down. Examples of exothermic reaction. Here, all this here, combustion, neutralization, blah, 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 changes of state. And also examples of endothermic reaction. Okay, like this few here, boiling, evaporation, all these are endothermic. Dissolution of certain salts, endothermic. Certain chemical reactions are also endothermic. So yeah, that's all we covered. Next week when we return to class, I'll return the MST papers to you, or at least let you take a look. Any questions from anyone? No? No? Now, as I say, this session is recorded, so the recording will come up, I think about half an hour after the meeting. All right, so if you want to review, go ahead and look at the, watch the video. All right, last call. Any questions for today? No? Okay, yes.
The mirror, right?
Yep.
Okay.
Yeah, the link is for Miro. You can access it.
Okay.
Yeah, it's right within this chat box. Okay, I'm good. Oh, by the way, I'm going to leave the content in Miro at least for the next few days because I'm going to have another class as well with, yeah. So I'll probably erase some of the stuff. So try if you want to access it like today or tomorrow. That'd be the safest. Okay, so if there are no further questions, then that's all for today. So I'll see you next week in class. Okay, goodbye.